Learning Goals. Welcome to this learning session on binomial distributions, Introduction and Basics. In this course, we shall address probability distribution basics, understanding binomial distribution, visualizing trials and expansion, calculating binomial probabilities, applying binomial concepts. There will be a quiz at the end to test your knowledge.
Introduction to probability distributions. A probability distribution of a random variable x is a comprehensive list of all possible numerical outcomes x can take, along with their associated probabilities. This systematic representation allows for a clear understanding of the likelihood of each event occurring. For a distribution to be valid, two key conditions must be met. First, each probability must be between 0 and 1 inclusive, and second, the sum of all probabilities for all possible outcomes must equal 1. This ensures that all possible events are accounted for. Consider the simple example of flipping 3 fair coins. The number of heads, x, can range from 0 to 3. The probability distribution would list the probability of getting 0 heads, 1 head, 2 heads, and 3 heads, which are 0.125, 0.375, and 0.125 respectively. This type of discrete distribution is foundational to many statistical analyses. Defining binomial distribution. A binomial distribution specifically models experiments where there are only two mutually exclusive outcomes for each trial, success or failure. This binary nature is crucial, as it simplifies the analysis of repeated independent events. For example, if you roll a standard 6-sided die and define getting a 6 as a success, then any other outcome, 1, 2, 3, 4, or 5, is considered a failure. This clear distinction allows us to assign probabilities to each outcome. In binomial probability, the probability of success is denoted by P, and the probability of failure is denoted by Q. A fundamental rule is that P plus Q equals 1, meaning that success and failure are the only two possibilities for any given trial. This framework is widely used in fields like quality control, where items are either defective or not defective. Probability tree diagrams visually map outcomes and probabilities in a sequence of trials. They are particularly useful for understanding conditional probabilities. Probability tree diagrams are powerful visual tools for mapping out all possible outcomes of a sequence of trials and their associated probabilities. Each branch represents a possible outcome, and the probabilities are multiplied along the branches to find the probability of a specific sequence. Consider throwing 2 dice as 2 independent trials. The first throw has outcomes 6, success P, or not 6, failure Q. From each of these, the second throw branches out again with 6 or not 6. This creates 4 possible end outcomes: 6, 6, 6, not 6, not 6, 6, and not 6, not 6. The diagram clearly shows that there are 2 ways to get exactly 1 6, either 6 on the first throw and not 6 on the second, PXQ, or not 6 on the first and 6 on the second, QXP. The total probability for exactly 1 6 is the sum of these paths, 2PQ. This method is particularly useful for visualizing conditional probabilities in more complex scenarios. Binomial expansion for repeated trials. The algebraic expansion of P plus Q squared provides a direct way to calculate probabilities for 2 repeated trials of 2 mutually exclusive events. This formula is a cornerstone of understanding binomial probabilities without drawing a full tree diagram every time. When expanded, P plus Q squared equals P plus 2PQ plus Q squared. Each term in this expansion corresponds to a specific combination of outcomes. P squared represents the probability of 2 successes, Q squared represents the probability of 2 failures, and 2PQ represents the probability of exactly 1 success and 1 failure. This formula is particularly useful because it directly reflects the structure of binomial experiments. For instance, in a series of coin flips, p squared would be the probability of getting 2 heads, q squared the probability of 2 tails, and 2pq the probability of getting 1 head and 1 tail, regardless of the order. This concept can be extended to p plus qn for n trials, forming the basis of the binomial theorem in probability. Worked example, calculating probabilities. Let's apply these concepts to a practical example. Imagine 2 identical bags, A and B, each containing 5 white beads and 3 red beads. If we randomly select 1 bead from bag A and 1 bead from bag B, we can calculate various probabilities. First, we define getting a white bead as a success. The probability of success, P, is 5/8, 5 white beads out of 8 total. Consequently, the probability of failure, Q, getting a red bead, is 3/8. Notice that P plus Q equals 5/8 plus 3/8, 1, confirming our probabilities are correctly defined. To find the probability that both beads are white, we multiply the probability of getting a white bead from bag A by the probability of getting a white bead from bag B. Since the bags are identical and the selections are independent, this is P how P equals P squared equals 5/8 to 5/8 equals 25/64. This represents 2 consecutive successes. To find the probability that exactly 1 bead is white, we consider the 2 possible scenarios, a white bead from bag A and a red bead from bag B, PQ, or a red bead from bag A and a white bead from bag B, Q star P. Summing these gives 2PQ equals 2 and a 5/8 nor 3/8 equals 30/64. This demonstrates the application of the 2PQ term from the binomial expansion. Practice problems, applying binomial concepts. Let's test your understanding with a practice problem. Alice has a biased die, where the probability of rolling a 6 is 0.2. She rolls the die twice. This scenario perfectly fits a binomial distribution, as each roll is an independent trial with 2 outcomes, getting a 6 or not getting a 6. For this problem, the probability of success, getting a 6, is p equals 0.2. Consequently, the probability of failure, not getting a 6, is q equals 1 minus p equals 1 minus 0.2 equals 0.8. These values are crucial for calculating the probabilities of different outcomes over 2 rolls. To work out the probability that Alice gets exactly 1 6 in 2 rolls, we use the 2PQ term from our binomial expansion. This accounts for getting a 6 on the first roll and not on the second, or vice versa. So the probability is 2 and 0.2 and 0.8 equals a 0.32. This highlights how the order of success and failure matters in the calculation. To work out the probability that Alice does not get a 6 in either of the rolls, we are looking for 2 consecutive failures. This is represented by q squared in the binomial expansion, so the probability is 0.8, 0.8 equals 0.64. These calculations are fundamental in understanding risk and chance in various real-world situations, from games to scientific experiments.
Summary. Well done. You have completed the course Binomial Distributions, Introduction and Basics. You should now be familiar with Probability Distribution Basics, Understanding Binomial Distribution, Visualizing Trials and Expansion, Calculating Binomial Probabilities, Applying Binomial Concepts. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.